So good morning everyone, we shall continue the lectures. Last time we finished off where we discussed integral time scale and we defined it as the memory of turbulent flow. How does the flow remember itself from a past state? Okay. If this integral time scale is large, then fluctuations in the flow are very slow and the flow correlates with itself for a few seconds or so backwards. But if this integral time scale is small, then the flow changes too quickly, or the fluctuations change too quickly. So it doesn't correlate with itself. Okay? Now, today I want to discuss another exciting and important relationship or mathematical relationship in turbulent flow, and I'll do it here. The autocovariance and twice the frequency spectrum form a Fourier transfer pair. Okay, well, autocovariance we've seen before. Autocovariance R is just a function of S. What was S? Time shift. Okay, so it's a function of time shift. But then I'm saying something about frequency spectrum. Why am I talking about frequency? Well, it looks like a new domain or space in which I want to analyze turbulent flow. The reason it's appropriate to talk about frequency is because fluctuations repeat themselves. Agree? Like eddies come and go at a different basically period or frequency. That's why it's very, very appropriate to think about turbulence in the frequency domain. Like all these eddies and fluctuations could happen at low frequency, could happen at high frequency. So they are very, very related. The frequency spectrum is very related to turbulence. Let me define a couple of things here for you. Let me define frequency as we know it in physics. For example, F. What's the unit of frequency? Hertz. Hertz or per second, right?
Yes.
So the unit of frequency is hertz or per second. Omega is known as also known as frequency, but it's defined as 2 pi times f. What's the unit of omega?
Radian per second.
Is radian per second. So not much has happened. I've just multiplied f, frequency, which was hertz, by 2 pi. So think of it as sort of an angular frequency or something. It's the same information. Now, I said something about autocovariance and frequency spectrum forming a Fourier transform pair. How many of you have heard of Fourier transform before? Fourier transform in undergraduate or other courses. It has to do, Fourier transform has to do with frequency. Now, mathematically speaking, we say two functions form a Fourier transform pair if this relationship holds. So look very carefully. I have one function, autocovariance, in the domain of time shift, Rs, right? R is a function of time. If I multiply by exponent of minus I omega s, and I here is the complex number, okay, exponential of the minus I omega s, times ds, and I integrate this as a I integrate it over time, or all possible times, put a factor of 1 over pi, I calculate something. Okay? Now this is a new function. This new function is no longer a function of time, it's a function of frequency, right? It's a function of omega. And omega appears here in the exponent. See that? There's a little omega here. But after I take the integral, s disappears. The time information disappears. I only have a function which is as a function of frequency. Now, this new function, which was a function of omega e, a frequency spectrum, if I integrate that over frequency now, but I multiply by e or exponential of I omega s. So see, the minus sign is missing. Up here I have minus sign on the exponent of e. Here I have no minus sign. But omega s are still here. Now this integral is over frequency, it's no longer over time. So it's over all possible values of frequency, and here time is a constant, s, or time shift. If I do this, put a factor of 1/2 in front of it, I calculate Rs. See what happens? These two functions are related by an integral, going back and forth. So think about it this way. This function is actually here, right? And this function is here. They are interchanged. And the only difference was this negative sign in the exponent as I integrated each, and the constant I put in front of it. If any two functions in mathematics relate in this way, they are Fourier transform pairs of one another. Which means, which is a very profound result. This means that frequency and time shift are actually related. Frequency and time shift are related. So let me use this eddy burst example. I stand here in the floor. Remember we talked about that, and wind is coming. Well, if eddies vary very slowly, you know, like they modulate very slowly, the time shift is large, which means if an eddy comes and the breeze goes over my face, the next eddy comes, I have a good very long time sensation of these eddies coming. The time shift is large, the frequency must be low, or low, small. See? So large time shift, slow, small frequency. On the other hand, if eddies are bursting into my face very rapidly, the time shift is small. They come and go and come and go. Then the frequency must be high. They're related. Okay? And we talked that omega is frequency in radians per second. If you wonder how to calculate exponential e to the exponent of a complex number, you can use the Euler Formula. And this you must have seen in some advanced or preliminary calculus. So if you have e to the exponent of any complex number times a real number, this is going to be equal to the cosine of the real number x plus imaginary complex number I times sine of that real number x. Okay? In our case, we have omega t, or omega s, if you will, up here. We have omega s or omega t. So this omega t is a real number, and the definition is still important. The Fourier transform pair is actually simplified a little bit because the function sine is an odd function around 0, and I'll explain to you in the next page what I mean by that. It's an odd function. I sine omega s is an odd function. And it's integrated to 0. So only the term cosine of omega remains. Cosine of omega s actually. Cosine of omega s remains. Now, why is the frequency domain useful? There is a very important relationship that relates to variance of fluctuations. A fundamental property of the frequency spectrum is that for a range of frequencies, pick any two frequencies, omega A and omega B, 2 hertz and 4 hertz, anything, 6 hertz, 19 hertz. Pick a range of frequencies. If you integrate the frequency spectrum over that range, you're actually calculating a portion of variance of all modes in the frequency range in between omega A and omega B. You're actually calculating variance. You're calculating variance of U component fluctuation. So the area under the curve is related to variance. In other words, this integral gives the amount of variance due to turbulent fluctuations in that particular frequency range. Okay? Now, I can put a very nice picture to this. Let's put a picture to it. If you measure fluctuations in velocity in any turbulent flow, it's going to be very noisy. So if this is U, total velocity, put a probe here in this room and measure air velocity fluctuations. There's going to be lots of noise. Okay? This is a time series. And all of these fluctuations have some sort of total variance. Do you agree? There's a total variance associated with all of the fluctuations. I can think of the fluctuations coming in different frequencies. What do I mean by that? So, what I mean is, the signal could have a component of fluctuation which it varies very slowly. I'll call this low frequency contribution to variance. Okay? So some of the variance is caused by the very slow motions. On the other hand, there could be variations that have higher frequency, all the way up to the highest possible frequency. Some of the fluctuations in this signal are caused by really, really high frequencies. And everything in between. I mean, I could have many different frequencies possible. If you think about it, if you add them up, then finally you get the original signal. I mean, let me put it this way. If this was frequency number 1, and this was frequency number, let's say, n, could be many frequencies. The top one was associated with low frequency contribution. This one was associated with high frequency. Contribution to variance. If I only add one and the first and the last one together, I should get only 2 modes of the original signal. So this would be low plus high frequency contribution to variance. Of course, I only used 1 and n, right? If I used all other possible frequencies in between, I would get the very original signal, okay? But I was just demonstrating to you what I mean by component of, frequency component of fluctuations. And what I'm claiming here now is if you integrated this frequency spectrum, I mean the frequency spectrum is some sort of a curve like that. So you can think of that as energy spectrum omega, and this is a function of omega, right? It's a spectrum, is a function of frequency. If I integrate this between 2 frequencies, omega A and omega B, the area under the curve, is the component of variance, but only in that particular frequency range. If I want the total variance, I can integrate all of this curve, and that gives me the total variance of U. So frequency and time shift are very related. Or omega and S are related. Now, if I want the total variance, I have to, as I said, integrate all of this energy spectrum over all possible frequencies. The smallest possible frequency is 0. That means a steady flow. There's no eddies, right? No eddies, no fluctuations. And then infinity means as eddies as fast as they could occur. This has to be, ought to be the total variance. You could write some other relationships too. I mean, it's not too difficult to show that the integral time scale, integral time scale is related to the energy spectrum at frequency 0 and total variance. You can show some of these relationships. Okay. I'm not going to prove it, but everything is related. I will now slowly navigate my way into multi-point correlations, random fields, and ensemble averaging. So let me discuss this concept. When we deal with transport equations, we often have to take derivatives. right? A transport equation is a differential equation, right? You have derivatives of time and derivatives of space. So the question is, how do we take derivatives? By definition, taking derivative is taking a limit. And if you are taking a limit of time, delta t, as it goes to 0, the ratio of the difference at any given time plus delta t minus t, this could be velocity, u component velocity, over time difference. As the limit delta t approaches 0, the limit approaches the derivative. We know this from calculus. Not all random processes are differential. I mean, this limit may not exist for a lot of random processes, but for turbulent flow, it often exists. Which means that velocity is a continuous and differentiable function. That's why you can take its derivative. That's the very requirement we need to be able to take a derivative of something. Think about it this way. U varies very continuously, and it's very differentiable with time. I mean, even though there are fluctuations, right? But this signal is continuous, smooth, and differentiable. You know what I'm saying? It's not like, so this is differentiable. But some other random processes, maybe not in turbulence, but some elsewhere. I mean, call them something else. Call them some F, some process F. It may be random, but it could be highly discontinuous. Right? This random process F is not differentiable because it's highly discontinuous. It's not differentiable. But in turbulent flow, velocity is. Note that here I'm talking about differentiation with respect to time. Okay, with respect to time. That means as time goes on, velocity changes. But I could also be talking about differentiation over space, which I will in a little bit. The question is, what is the mean of a derivative, right? Remember this symbol we talked of as a statistical mean. You must remember this. Statistical mean. The question is, does the mean of a derivative exist? Okay, and I claim that it does. Why? Because taking the mean operation expands. It's a linear operator, right? It goes in and out of linear combinations of terms. So this mean operator actually goes inside the limit, and then it becomes the mean of velocity at time t plus delta t minus mean of velocity divided by time difference. So what is on the top? It's actually the differential of mean velocity. So I just found a very important result, and that's the mean of the derivative of a random process is also equal to the derivative of the mean of the random process. Well, now here's a quiz for you. So after I take the averaging, after I do the averaging, I'm telling you there is a differential of velocity with respect to time. What is that differential for a statistically stationary process? Zero. Because statistically stationary was a process where the statistics did not change with time. Okay? So think about this. For steady flows, steady turbulent flows, this must be zero. But not all turbulent flows are steady. They could actually vary with time. Right? If statistically not stationary, the derivative is not guaranteed to be zero. Lots of flows are exhibit that. I mean, think of the atmosphere. I mean, the atmospheric state changes diurnally. Now is different from 1 hour from now, is different from 2 hours from now, right? Then in the afternoon, the atmospheric state is changing, it's transient. So that's very good. The next topic is random fields. In all of physics, the term field shows up all the time. What is field?
The zone in which we can experience that process, I guess.
Yeah, it's
influence. A space in which we can feel the influence of.
Yeah, right? So field gives you the dependability of a process on the domain. It could be a spatial domain, it could be time domain. Most quantities in physics can be thought of as fields. We have electric field, magnetic field, gravitational field. And there's lots of great field equations. Like Einstein's relativity is a field equation. He thought of the universe as a field of mass and energy and gravity, space and time. And he could come up with all those wonderful theories. So the concept of field is very powerful in physics. And we use the concept of field in turbulence too. We think of velocity as a field because it could vary with space and time. So it's actually a time and space dependent random field. So is the velocity fluctuation. Because if you remove the mean of velocity from the instantaneous velocity, you get the fluctuation. So they're all vector fields. So this is a vector field. The instantaneous velocity, these two are also vector fields. They change with time and space. Like in this room, for example, the air velocity can change. And what we've been doing is we've been taking statistical approaches to calculate some statistical parameters here. We have done one-point multi-time statistics, which was the autocovariance, right? You can look at this field and see how this field is correlated with itself at a previous time, right? So that was an example of a one-point multi-time. There are also examples of one-point and one-time statistical parameters you can calculate or estimators. One is the covariance of fluctuations in different directions. Now, here it's the covariance of velocity, let's say u fluctuation, simultaneous with the v fluctuation. How are the components of fluctuations related? This is one time, one point, because I'm looking at one point in space and I'm looking at one time. But then what is varying if it's one time? Well, remember your ensemble averaging. So you repeat the experiment, and exactly at that moment, you calculate the covariance. And think about this, if I could repeat this day, right? Right now it's 10:34, right? I could come here, measure the velocity in this direction and that direction, 1034. Let's say the day repeated itself. It never does. But let's say it did. I come here again at 1034, do that measurement, and I repeat this many, many times. That's why I say it's a 1.1 time. This was the same point, and it was always at 1034. Okay? This covariance is computed for every spatial location in the fluid field. If you think about it, it's not just here that I could do this calculation. I could do this calculation here, I could do this calculation here, everywhere. There is another field that results out of taking the covariance. Okay? It's a very profound concept. So again, one time, 1 point, which means x is unique, and it means time. X or space is unique, and it means time is unique. It's just different experiments that I'm doing. And then these covariances that I can calculate are quite a few. I could do U, V, I could do U, W, and I could do V, W. If I'm looking at different components, I and J, like 1 and 2 or 1 and 3, right? It would be U and V, U and W, or it could be 2 and 3, V and W. But it could also be the same. If these are the same, I'll get U squared, the same as variance, right? U squared, V squared, and W squared. And in fact, VU, VW, VU, WU, and WV. So, I mean, here I'm thinking of it as I can, if I swap these components, I mean, from the point of view of symmetry, it could be the same, but anyway, it could be different. So if all the possibilities add up to 9 cases, right? But in fact, if you swap, nothing happens. You calculate the same quantity. These 9 combinations of 1.1 time statistics are known as Reynolds stress. Reynolds stress. And Reynolds stresses are... Can you suggest if a Reynolds stress is a tensor or a vector? Tensor. Why?
2
directions, right? It requires 2 directions for definition, U and V, or U and W, and so on. I mean, X and Y, and so on. Okay? It's a very interesting concept. I could take the mean of the time derivative of velocity. I just did that up here, right? It's the same thing as I showed you here. Mean of a derivative with respect to time is the derivative of the mean with respect to time. That. Let's talk about space. For space is the same. You could take the derivative of a velocity component with respect to a specific spatial direction. It could be x, it could be y, it could be z, it could be x1, x2, x3. And here the same. The mean of a spatial derivative is the spatial derivative of the mean. It's just a fact. So now we know what those derivatives are. They also apply to means. Now let's talk about a statistically stationary, homogeneous, and axisymmetric turbulent flows. I defined for you a statistically stationary before. These are turbulent flows in which statistics do not change, regardless of whenever you calculate them. If you calculate mean or variance of flow in let's say in this room, if you measured it now for 5 minutes, some number, if you measured it, 10 minutes from now, for another 5 minutes, it's the same, 15 minutes, doesn't matter. The statistics do not change with time. So these we know as statistically stationary flows. So just repeating the definition from last time, stationary, if all statistics are invariant under a time shift. There are other conditions that may happen. They're statistically homogeneous if all statistics are invariant under a shift in position, which means that if the airflow in this room is statistically homogeneous, if I measure some variances and means here, and at the same time I measure them here, I calculate the same thing. And a lot of flows exhibit that, to a very good level of approximation. Think of atmospheric flow. Atmospheric flow over an open field. Let's say you go to a soccer field, right? You put an anemometer there, measure wind speed, average wind for 5 minutes. It's the same as measuring it, let's say, 20 meters this way or that way. Like open fields and atmospheric flows are statistically homogeneous. There's no reason why wind should be different here than here. Oceanic flows may be the same. Like flows in general over a smooth surface at very large scale are statistically homogeneous in the sort of horizontal direction, right? Of course, if you go up into the stratosphere, things may change. But horizontally, it's very homogeneous. Also, a field is statistically axisymmetric if all statistics are independent of the circumferential coordinate. And this one is very interesting too. I will put a picture to it. Axisymmetric. Actually, no, I won't put a picture to it. I put a picture to the next one. But axisymmetric means it applies to some sort of circular flows, which anytime there is sort of circular motion, let's think of a hurricane, right? Or a swirl, or a spinning piece of fluid. It doesn't matter where you do your measurement around the circle. So around an axis, around the circle, statistics are the same. A lot of jets, plumes exhibit that behavior. And these are special cases that can happen which will make the analysis of the flow very simple. Think about it. Most statistically stationary flows are sort of steady flows. So the Navier-Stokes equations simplify, and we can deal with them nicely. Homogeneous flows are like flows near walls, like boundary layer flows. Then we can treat those as a special case, then simplify the problem. Axisymmetric flows like jets, right? Again, the equations simplify. These are different levels of simplification that happen. And we will actually have dedicated chapters for each one. So far, so good. Questions? Good. The next important concept is isotropic and anisotropic flows. And this one is a big deal, especially in turbulence modeling. It's a big deal. If the field is also invariant under rotations and reflections of the coordinate system, then statistics are isotropic. I'll put a picture to it. For instance, in a statistically isotropic field, it doesn't matter which two components you look at. If you calculate Reynolds stress between component 1 and 2, or 1 and 3, or 2 and 3, it doesn't matter. They're all the same. Why? Because if I rotate it, the coordinate system, I could go from U1 to U2. I'll show it to you in the picture. Otherwise, the field is statistically anisotropic. I'll put a picture to it now. Let's say you have a flow system. Say, air in this room, or the atmosphere, or the ocean, and the flow is coming. There are all kinds of fluctuations. You know, the flow has lots of eddies, big or small. It's a turbulent flow. Let's say I have my coordinate systems defined this way. So x points to the right, y is into the page, and z is upward. According to this coordinate system, I can measure all of these. Like all the variances and all the covariances. The same system. Now I want to analyze to see exactly the same system. But this time I want to rotate the coordinate system. I want to rotate it. Let's say rotate, I don't know, the x-axis. If I rotated the coordinate system, the question is now if I calculate my variances and so on, would I obtain the same values as before? You see what I'm saying? Would I obtain the same variances and covariances or components of Reynolds stress? So if this system is isotropic, if isotropic, then this should happen. U, regardless of the coordinate system, variances of u, v, and w must be the same, and covariances must be the same too. It greatly simplifies things. If a flow is isotropic, it means that there's only two components of Reynolds stress, really. I either get the variance or I get covariance. All of the variances are the same, all of the covariances are the same, regardless of the rotational position of my coordinate system. It's a very interesting concept. And it's a very profound level of simplification we make to analyze turbulent flows. A lot of flows are very isotropic. Some flows are not. I mean, the atmosphere is not isotropic because in the vertical direction, it varies very differently than the horizontal direction. All kinds of environmental systems, water reactors, boundary layer flows, river flows, ocean flows, they're not isotropic. But a lot of times it is. I mean, in confined space, it may be. I mean, a combustion engine inside the cylinder, maybe in a confined space, it may be isotropic. It's a very, very useful approximation. In fact, a lot of the models that exist out there work based on the isotropic assumption. Any questions so far?
So are homogeneous and isotropic the same thing?
Very good question. No. I'll give you an example. The atmosphere is, think of it this way. Homogeneous means make no statement about the rotation of the coordinate system. Homogeneous, right? X, Y, Z. If I measure all the components of the Rayleigh stress tensor, gives me some numbers. Homogeneous just says, okay, if I do the same measurement here, I get the same values. Same measurements here. It did not allow me to rotate. See what's happening? But isotropic means now stay where you are, now you're allowed to rotate. It didn't say anything about translation of the coordinate system, right? One was talking about translation of the coordinate system. One was talking about rotation. In under special cases, it may be this, both may apply. I promised you to do multi-point correlation for you, because last time we did a multi-time correlation, autocovariance. Same position, measurements at different times. Now I want to say this. I want to define a new statistic which allows me to make two measurements at two different locations at the same time. This type of measurement we know as two-point correlation. Two-point correlation and one-time autocovariance is defined by this symbol now. So remember, it's still autocovariance because it's the flow compared against itself. You know what I'm saying? It's autocovariance, but this time it's 2.1 time. In the last lecture, it was 1-point multi-time. Okay. So I still use the same symbol R for this one, but now it's not only a function of time shift S. That was very simple. Now it's more complicated. It needs a lot of directions, specifications of directions, because the 2 points relative to one another. I mean, where are the 2 points related to one another? One point could be here, another point could be along the x-axis. One point could be here, another point could be along the z-axis, along the y-axis, right? Or it could be even, any spatial configuration. So I need some sort of vector R to tell me how these 2 points are related. I need a location. Still need a location because I could have my point, the first point here, the second point here, or I could have the first point here and the second point here. So the location of one of those points is also an input argument to this function x. And of course, the time is still there because there's no guarantee the flow will be steady, right? Think of ensemble averaging. I could do this for a transient process at the beginning of the process, in the middle of the process, at the end of the process. And I could repeat the experiment, right, like a million times. So it takes much more inputs. And on top, I have I and j, right? Which components am I interested in? Am I interested in u and v, or u and w, or v and u, right? I could look at any pairs of fluctuations between the 2 points. So that's why I and j are also. So it's overwhelming. There are 5 sort of input parameters
that go into the calculation of the autovariance.
We also know this as two-point correlation. And the really fascinating thing is that the two-point correlations allow us to calculate integral length scales. Okay, last time we talked about integral time scale, which says something about the time feature of fluctuations. Like if these eddies are very slowly or quickly, you know, how frequently are they coming at us? But we should do justice and also talk about the length of these eddies. Think of it this way: is the eddy small? Is the eddy big? Integral length scales give you information about the size of the eddies. But it's a little bit more complicated than integral time scales because size is directionally can be defined over a direction. Size has three components. You know what I'm saying? I mean, I could be talking about the size of this table in the x direction, in the y direction, in the z direction. So I should get at least three components. But for eddies, it's more complicated because eddies are nothing but fluctuations. In fact, I should be defining them over 9 pairs of possibilities, right? Think of, there's more than 3 directions involved. It's like pairs of 3 directions. So actually, there's actually 9 possibilities. So these all ties back into the tensor concept. So if you're interested in, let's say, direction 1, 1 along vector, this r vector, which is along E1, then this is the size of eddy that I get by integrating the two-point correlation from 0 to infinity. This integration is over space. It's no longer over time, right? But it's done at a specific time and location. So what's happening? I'll put a very nice diagram for you up so you can actually grasp the concept. Just be patient. So I should carefully say something about, so now you're integrating over space. So let me put this in a very nice diagram for you. Two-point correlation. Let me use the example of flow around the building. In the computer assignments, you see that I've measured airflow and turbulence of air on campus, on the roof of a building, and at street level. And if you read the assignment, the building of interest is the Rosansky Hall. So I have a building there, which is the Rosansky Hall. I had one anemometer on the roof of Rosansky Hall. And I had another anemometer on the requad, which was the sort of alleyway beneath. So this was the requad. I had one anemometer there. I'm measuring turbulent properties of atmospheric flow. So let's suppose I have wind coming in this way toward the building. The coordinates x, y, z. In a lot of environmental flows, x is along the flow parallel to the Earth's surface or ocean surface. Z is normal to the surface, so vertical height. Y is into the page. Now, if you think about it, I can calculate the two-point correlation because I have 2 anemometers. I can calculate the two-point correlation of fluctuations between the 2 anemometers. The first point is located here. So if you like, this is vector x. That's vector x locating the first point with respect to the origin. The two anemometers are positioned relative to one another with vector r. Remember I said point 1, point 2, and there's a vector connecting the 2 points. And it goes without saying that it means that the roof anemometer should be x plus r. Okay. And again, what was this sensor called? Ultrasonic anemometer. What did it measure? UVW at very high frequencies. So I could calculate the 2-point correlation. What about the integral? What about the integral length scale? The integral length scale required me to integrate over many possibilities over space. In fact, I need to measure over all possible values of r, right, from 0 to infinity. So the two anemometers is not enough. With 2 anemometers, I could measure just the 2-point correlation. I could do this with 2 anemometers. But if I want to measure the integral length scale, I need, how many anemometers do I need? Infinite number of anemometers, right? And I can put that in the picture for you. For the same measurement, oh wait a minute, so I should say this, can measure R. So this enables me to measure R, I, J, R, X, and T. This gets interesting. I had 2, but along that vector R, I need many other anemometers. And then this goes all the way to infinity. And then this is R. But remember, R is varying from 0 to infinity. So that's really interesting. And if I did this measurement and measured L, so with this setup, now I can measure L, let's say 1, 1 around so this is measured along R, right? Along vector R, and I'm measuring the first component of fluctuations in the x direction, u and u squared. Sort of loosely speaking, it tells me something about the length scale of eddies. I mean, sort of speak. That's how big the eddies are. They could look like this, maybe. They could look like maybe this. It gives me that component, the that dimensional component of the eddy in that direction. You see what I'm saying? I can't make any statement on how big it will be in this direction, right? I can only say something that it's somehow that big in the direction of r. Sounds very depressing, right? I mean, it means that you can't measure anything. If you want to have a good understanding of turbulent flow, you need infinite sensors and you have to measure it. It's not possible, right? So, as depressing as it sounds, it's not that bad, because in the following discussions and lectures, there are lots of other principles we can use to obtain maximum amount of information from a flow by putting in minimum number of sensors. We can do that. So if you're patient, you will see all of those tricks. So to close this discussion on the integral scale, so we live in a three-dimensional, four-dimensional world, space and time, right? Space and time is all there is, and so eddies too should have characteristic times and length, or integral times and length. This is sort of a representative of how quickly they occur and how big they are as they occur. You know, these are known as the integral scales. I should now talk about wave number. Have you heard of the term wave number before? What is a wave number? Anybody want to try? What is a wave? We know what wave is. It's some sort of oscillatory motion in space. The first thing I want to define is the concept of wave number vector. The wave number is the spatial frequency of a wave, and it can be recorded in either cycles per unit distance or radians per unit distance. I mean, there is no reason that the concept of repetition should only occur in the time domain. Repetition can also occur in the spatial domain. Geometrically, the space can repeat itself. So we can talk about some sort of frequency in space, not in time. It's a very nice concept. And I'll show you a picture for that shortly, but let's put a definition to it. What is this symbol in Greek? Kappa. Kappa. We define wave number using kappa, and what is this symbol in Greek? Lambda. Lambda. Yeah. And wave number in cycles per unit distance is known as this kappa, or lambda. Wave number as cycles per or radians per unit distance is also kappa, but here we have 2 pi on the numerator. So it's the same symbol, but it can be calculated in different ways. You have to be careful which one you employ. But now I want to show you the picture. Now I want to show you the picture. I told you that a space can repeat itself too. Can you give me an example of how space repeats itself? There's one example in this room. Just look around. What's repeating itself? The lights, right, repeat themselves 4 times. The chairs, right? Think about it this way. Wave number is known as frequency in space, not time. And let's say we use the example of chairs, right? There are so many chairs in this room. 1, 2, 3. There are so many chairs in this room. What about, I mean, in the urban area, you know, you go out there and you see a lot of buildings that repeat themselves. Buildings, chairs, buildings. Do they have the spatial repetitions? Do they have to be solid, or they can also happen in liquids? Do you go surfing sometimes? If you look at the ocean surface, you get a wave, right? These waves in the ocean come at some sort of the spatial waves in ocean. I mean, by and large, these waves come with some spatial repetition. So here's the surfer. Okay, so a space can repeat itself. So when we talk about lambda, lambda is the distance between the repetitions, right? One chair to the next chair, one building to the next building, maybe one wave to the next wave. This is lambda, and kappa is just 1 over lambda. Basically, the number of repetition per unit space, right? If lambda is very small, then a space repeats itself much more per unit length, which is 1 meter. If the number of, repetitions are pretty large in size, then repetition per unit length is going to be very small because you divide 1 over lambda. Or if you want, 2 pi over lambda. So we have a sense of what wave number is. If you think of eddies, in the flow, eddies in the flow can also be spatially repeating themselves. I mean, the ocean wave I showed you, that was an eddy. The ocean wave was an eddy because it doesn't last forever. It forms and then moves and disappears. So these actually, you look at the clouds. Have you looked at the cloud instabilities in clouds? Sometimes you see the Helmholtz clouds, like multiple repetitions. So they're out there. Kelvin Helmholtz instabilities in the clouds. What is the units of kappa? If kappa is 1 over lambda, the unit must be per meter. And if it is 2 pi over lambda, radians per meter. So the unit units of wave number we also. Now I want to tell you the analogous situation with space. Remember the Fourier transform pair that related time frequency with time shift? Now I want to relate a spatial frequency with autocovariance or spatial shift in space. So analogous. How do I do that? There's another Fourier transform pair between autocovariance defined over a space shift and velocity spectrum tensor. I mean, things get a little bit more complicated because I have a lot of tensors here because now I need two directions to define all of these. Also, the integrals are no longer single integrals, the triple integrals, because I'm integrating over a space, and space has three dimensions. But it's the same relationship, right? So R is related to phi, which is the velocity spectrum tensors, and phi is also related to R. In this sense, R, here you're integrating over a space, exponent of E is minus I kappa R. So this time I have kappa R, there's no longer omega, kappa is wave number, spatial frequency. The constant in front of the triple integral is 1 over 2 pi cubed. Here I have the minus sign. It was here. Here I don't have a minus sign. I kappa R, right? And I'm integrating over wave number or spatial frequency. So all of these are the differentials, like dr, d kappa are three-dimensional differentials, because your cube space can be understood as having three components: dr1, dr2, dr3, or dx, dy, dz. The wave number 2, the space can repeat in itself in different directions, so to speak. Okay, so that's really exciting. And the same relationships hold between Reynolds stresses this time and the velocity is spectrum tensor. We are not really going to go really crazy and deep in the math. I'm never going to give you an exam problem which asks you to do this. But at a very high level, I want you to see the connections. Okay, so it's very exciting. Things highly related. Let me begin. So this is the final heading of this chapter. It's called Types of Averaging. I can get going and really quickly discuss all of this because we've done it before. We talked about statistical averaging, which was based on probability density function. So for this type of statistical averaging, you need a probability density function. Problem is you never have one in reality. So this is the very definition of statistical averaging from the mathematical sense. Then we talked about ensemble averaging, which is more practical to do. In this case, you repeat an experiment. You repeat an experiment a number of times, and then you take the average of that. That's way more practical to do. Another type of averaging is called time averaging, in which case you measure some signal over some time interval t, and then you calculate the average over the time in interval t. This type of averaging we know as time averaging. And we have the subscript t. If you remember, we said even ensemble averaging is not possible in reality. No experiments repeat themselves identically. So even this is not possible many times. Maybe in computer model you can, but in reality you never. But time averaging is very practical. We do time averaging all the time. And finally, there is spatial averaging, which you measure the quantity over different location space and then calculate some sort of average over a space. Okay? Like if I ask you, what's the temperature of air in this room? What would you do? You put many sensors in different locations, measure the numbers, give me an average temperature. This is some sort of a spatial average. Okay? So I want to now, there's 1 or 2 minutes, so let's see if we can do a quick problem from this chapter. It's a very short problem as usual, so let me do it very, it's very short. Do it, and then we'll done with it. I want to problem number 3, which gives you the autocorrelation function, rho s, which was a function of time shift. And I want you to show that the integral time scale for this specific autocorrelation function is 1 second. Okay? So autocorrelation function is 1 over 1 plus s squared. I want to show that the integral time scale is 1 second. Very quick. Exercise 3. If you remember, autocorrelation function usually decays with time shift, and then the integral of this is integral time. So I just have to integrate this. Integrate from 0 to infinity of rho s. Okay. So if you did this integral, the answer would be 1 second, which means that on average, by and large, the eddies last for 1 second. So if you were standing in front of this flow, every 1 second you would feel a new eddy coming to you. Okay, so just to demonstrate that you can calculate this. As part of the computer assignments, you calculate all of these 1-point multi-time statistics, and you will also calculate multi-point one-time statistics. So you calculate all of these autocovariances, and the data set is the anemometers that are on the roof and on the street level on the campus. So you will calculate these very shortly in the computer assignment. Sounds good?
Yes.
So timing is good, and we finished this lecture. So have a nice day. We'll see you next week with a new chapter, chapter 4.